For this look at contingency analysis, I'm using the car poll data, which is talked about in Chapter 12 of the Jump Start Statistics book. I'm going to go in Jump to Help. I'm going to go to the Sample Data Library. I'm going to go down to where it says carpoll.jump. I'm going to double click on that, and that'll open up a data table here that has the car poll data in it. As usual, it's not a bad idea to go to Analyze Distribution. I can bring in all of the variables that we have here, click on Y, click on OK, and then I'll see the distribution. I have about the same number of males and females. I have information about their marital status at the time of this poll. I have the distribution of ages represented in the poll. I have, I believe these are countries of purchase of automobiles, the size of the automobiles that they buy, and then the type of automobiles that they buy. If we were doing a two sample test or an ANOVA test, we could use age as the dependent variable, and we could use marital status. We could see who are married people older or younger than single people. We could do an ANOVA by taking the country of the car that they purchased and then seeing how old the people are. But in this case, what if we just want to do something as basic as comparing sex and marital status and find out whether or not in our sample we have a pattern that would tell us whether or not men or women have a tendency to get married more or less. I'm going to just go ahead and click out of the distribution at this point. And to do this, we're once again going to use the Fit Y by X platform. I don't know if you've noticed this diagram down here, but what it's showing us is that actually, depending on the type of data that we're using, there are 4 different types of analyses that can be done with Fit Y by X. We've looked at the one way predominantly, that's 1, 2 sample, and ANOVA. We're now going to look at contingency, and this is telling us that contingency works when we have a categorical variable against a categorical variable. After we finish this and we go on to correlation, then we'll be getting into the realm of bivariate relationships. Ultimately, later in the semester, we'll do logistic, and that is when we have a set of continuous data that is actually predicting a categorical outcome. If you ever get a curve that looks like this, it probably means at this point in time that you put in the variables up here backwards. So try switching them and then you'll probably get it right. So let's say, does the gender or sex predict the marital status? Or are they related? So in this case, we are saying that we think one variable is influencing the other. We're saying that we think that there is an X and a Y. There's a response here. So I'm going to go ahead and click on OK. And I immediately get what's called a mosaic plot. Down on this axis, you can see that the bars are a little bit different size, and that has to do with the sample sizes of how many males and females we have in this particular sample. On this, we see our response variable of single versus married, and again, we're seeing what is the overall breakdown. That's where this little line is here. That's the midpoint line given the entire sample. And then these 2 lines here, notice that actually when I click on one of these, it highlights the rows in the data table. These lines here are determined by the percentage of that group in that particular category. So the percentage of males that are married. I can also right-click in this, and I can say cell labeling, and I can say show count or show percent. So here's the percentage is 61.2 for male and 38.8 for female. Sorry, single versus married under male. And then for female, we have 68.8% and 31.2%. Notice that this is still highlighted. I can go back to the data table here. I can say rows, clear row state, just to get rid of that extra highlighting. Once we have these percentages here, you can see that the same information is presented here in the contingency table, just in numbers. However, don't get tripped up by the fact that they put sex on the y-axis and marital status on the x-axis here, just backwards from here. Why JUMP decided to do that, I do not know, but you can see that there are the same information here. So if this is marital and female, then married and female is 68.8. And I got my rows again here, so I need to clear my row states. Now, what is the hypothesis that we're actually testing here? It is, in fact, that these probabilities are the same. Let me go to my prepared PowerPoint here. So the null hypothesis is that the probability of being single, or you could also say being married, based on sex is the same. So regardless of whether you are male or female, you have about the same chances of being single. Regardless of whether or not you're male or female, your chances of being single. So what are these boxes representing? Your chances of being single. And you can see that male and female, those probabilities would be about equal. The alternative hypothesis is that the probability of single based on sex is different. So if we were to have a situation like this, you can see that even though we have a lot more married people than single people, we still have the same probability of being single. These blue boxes are still about the same size. So we would probably end up not rejecting the null hypothesis. And this situation could also be exactly the same. But if we had this situation here, where if you're female, you have a much higher probability of being married and a lower probability of being single, versus being male, where you have a much lower probability of being married and much higher probability of being single, then we would probably end up rejecting the null hypothesis and saying that the probability of single based on sex is different. And just as we have the possibility of a one-tailed test where we would specify that we thought one of these was going to be different in a specific way, for example, it is true, I believe, in the general population that fewer men are married than women, although I may be wrong, then we could make the test so that it went in that direction. Okay, I've returned to JUMP here, and I'm going to close out that contingency table, and now you can see that JUMP automatically gave me the tests in this case. And so the likelihood ratio and a Pearson test, which are very similar, I rarely ever see any differences in those. Those are testing the hypothesis that these probabilities are the same. So that's a null hypothesis. And you notice right here we have yet again something that says probability. And this time the distribution that's being used in the test is the chi-square. That's why this is often called a chi-square test. And you can see that our number here is 0.165, which is greater than 0.05. So we would not reject the null hypothesis. In other words, we would conclude that even though we are seeing differences here, that in fact those differences are not large enough for us to conclude that they're really in actual fact in the overall population the difference between the rate of marriage between men and women. When you only have two levels in each category, so in other words a 2 by 2, you can use something called the Fisher's exact test, and it will actually spell out for you exactly what the alternative hypotheses are for a left-sided test, a right-sided test, and a two-tailed test. So what I was saying earlier with the PowerPoint, we were doing a two-tailed test, and here we were testing whether or not the probability of marriage status as single is different across sex, male and female. And again, we concluded that no, it's not less than 0.05. And even if we said that the probability of being single is greater for men, which we do believe may be true in the general population, we still didn't see that in this particular sample that we got. We didn't get less than 0.05 here, and we're able to reject that null hypothesis. Oh, I hear that airplane going overhead. Should I press my air noise button? Okay, let's test whether or not the marital status has any influence on the type of car which is purchased. So I'm going to say analyze, fit y by x. I'll take marital status as my x factor, and we'll take the type of car as the y. I'll click on OK. Now with this mosaic plot, I now have 3 levels on my y-axis and 2 levels here. So when we scroll down, you'll see that we do not have the same version of the Fisher's test available to us. Looking again, I can right-click here and I can say cell labeling. I can put in the percentages, and that gives me a quick way of saying, okay, do I really think, are these probabilities going to turn out to be the same? And my initial feeling would be that probably for sporty cars, a lot more single people buy them than married people. And family cars, a lot more married people buy them than single. And as far as work-oriented cars go, it's about the same. And so do the p-values bear this out? So I'm going to close out my contingency table. You'll see that for this, I'm only getting the standard tests of likelihood ratio and Pearson. And in this case now, we can see, yes, indeed, we're going to reject the null hypothesis. The null hypothesis is that regardless of married or single, we're going to find that the probabilities in all of these are the same. In other words, this would have to be 23 and 23, this would be 60 and 60, then this one is 16 and 16, something like that. And just as in ANOVA, when we reject that null hypothesis, all we're saying is that at least one of the probabilities in one category are different, not that all of them are different. And then it's up to us to figure out which one may or may not be different. When you look at the jump menu here, you're going to see a whole bunch more tests that are available here. Those would be for specialists for a Stats 2 course, and I would say you really don't need to worry about those at this point in time. And what we've done here is more than sufficient. So for the quiz, I'm going to put one question on the quiz. What you should do is you should see whether or not marital status has an influence on the size of cars that people buy. And so make sure that you check out the data here just using the same procedure that we did, and then you'll be able to answer that question on the quiz.